Hello and welcome. In this video, we're going to take a look at a funny name theorem. It's kind of helpful along with the limit laws in order to evaluate the limit of a function just by using some basic operations and not having to calculate it numerically. Now, it's called the squeeze theorem, and you'll understand why, but it may not be immediately apparent without some sort of illustration. So the squeeze theorem states that if f of x is less than or equal to g of x, which is less than or equal to h of x, if that's the case for x values near a, except potentially at the value x equals a, and if we know that the limit of f of x as x approaches a is L, and the limit of h of x as x approaches a is also L, then we can produce the result that the limit of g of x as x approaches a also equals L. Now, like I say, it may not be immediately apparent why it's called the squeeze theorem, but it might help to draw some sort of illustration here. Okay, well, I'm just going to draw a couple functions here in the first quadrant, and I'm going to assume a is some value here that's a positive number. Put that here, and we also are talking about the values of these functions approaching L, so we should put L somewhere along the vertical axis for y here. Now, we'll start off with the blue function f of x, and you can see that it is the smallest valued function of the three, so it should be at the lower end of my graph. But we do have this condition where the limit of f of x as x approaches a should be equal to L. So we are pointing towards a target. Whether or not that point exists, our target is at this sort of point here, a comma L. So we can draw as crazy of a function as we want. Just make sure it's kind of towards the bottom of the screen. And sure enough, I've actually maybe included the point here. It seems to be getting closer and closer to a y coordinate of L, and we can make the function y equals f of x as close to L as we like by choosing x values sufficiently close to a. Okay, now let's take a look at our second condition, which is the green function. The green function needs to be the largest valued function of the three, and it needs to be also approaching the value of L for x sufficiently close to a. So let's put that on the graph here now as well. Okay, green function should be near the top of the graph since it's the largest. It needs to also be approaching L, and it can do whatever else you want. Just make sure that we still have this idea of the limit. The green function, which is y equals h of x, can be made as close to L as we desire by choosing values of x sufficiently close to a. All right, now there's only one other condition. And when I keep saying condition, imagine that everything here with the if word are conditions. And then below that, we have one statement, which is our conclusion. So let's see, the remaining condition that we haven't talked about is that our function g of x is supposed to be somewhere between f of x and g of x. It's not the largest valued or the smallest valued. It was always going to have to be between f of x and and h of x for x values near a. So I mean, it could actually cross functions somewhere out here, but as we get closer to a, we have to make sure that g of x is between h and f. So why don't I just start off with some sort of graph? It can do all kinds of weird behavior as long as it's a function. And you see how if it has to be between the other two functions, this is where the idea of the squeeze comes in. The green function and the blue function are squeezing the red function, and the red function is forced to pass through this little narrow gap here. And so as a result, since the green and blue functions can be made as close to L as possible, as we desire, the red function is going to also end up getting as close to L as we desire for x values near a. And that's the result. The result here is that the limit of g of x as x approaches a must be equal to L if it is squeezed between f and h. Now, where is this going to be useful? We've already looked at some limit laws, and limit laws are very useful for evaluating the numerical value of a limit, provided that it exists, especially for rational functions. But we can look at other kinds of functions that aren't rational, things, for instance, like trigonometric functions or exponential functions or absolute value functions, things that our other limit laws weren't quite as able to apply. So maybe we'll just look at one quick example where this could be useful. Okay, here we've got an example of a limit, and it's limit of the function 2 plus t squared sine pi over t. And we're trying to take the limit as t approaches 0, and some of the other strategies that we've looked at with limit laws don't really seem to apply here. This isn't a rational function, definitely also not defined at t equals 0, since pi over 0 would be undefined. But what we do have is a nice oscillating trigonometric function, sine of pi over t. And a nice thing about the sine function, and also its sibling cosine, is it has a range of values only from -1 to 1. So it's bounded above and below by 2 values. And so we could just say sine of x for any value of x is always bounded above and below -1 and 1. And this is an inequality with 3 functions. And remember, with inequalities, you can add anything you like, in this case, adding it to all 3 functions, and you can multiply by any non-zero value, multiplying all 3 functions. But if you multiply by a negative value, then we have to change the direction of the inequalities. Now, one thing we can do right off the bat is, since x can be any value in the sine function, and this inequality is still true, we can decide to replace x with pi over t to match the trigonometric function as it is written in our example. And we still have the same inequality just because of the range of the sine function. Okay, well now, because we have 3 functions here and I want to multiply by any non-zero expression, well, I'm taking the limit as t approaches 0, but that doesn't mean that t equals 0. So that means that t squared is a non-zero expression. And we can multiply all 3 functions by t squared, and luckily t squared is always positive, and so it doesn't change the direction of the inequalities. So manipulating this inequality, we now have negative t squared less than or equal to t squared sine pi over t less than or equal to positive t squared. Now, the goal with doing that is so that the middle function here, t squared sine pi over t, begins to look a little bit more like the function in our example. The only thing that's missing is 2, but 2 is a value that we can add to all 3 functions, and that doesn't change the direction of the inequalities. So then we end up with adding 2 minus t squared, 2 plus t squared sine pi over t less than or equal to 2 plus t squared. And now you can see that this function here in the middle, that is corresponding to the one in our question. And we have 2 functions on either side, one being a lower bound and one being an upper bound. And let's see if we can meet all of the conditions of the squeeze theorem. We've already met one condition, which is going to be having our function g of t sandwiched between 2 other functions. We could call these other functions f of t and g of t. Now, another condition, after having this inequality condition, if we look back, we need to have these other remaining conditions that the limits of f and h as x approaches the value, in our case 0, both must be equal to the same value L. So we're going to take each of these individual equations, the individual functions, 2 minus t squared, and take the limit as t approaches 0 and see what we end up with. Sure enough, easy to evaluate, is just equal to 2, just by using limit laws there. And on the right hand side, take the function 2 plus t squared and take the limit as t approaches 0 there, and you see that's also equal to 2. It's worthwhile to make sure you've met all the conditions. We've got the condition of g being sandwiched between f and h. We've got the condition that the limits of f and h as x approach 0 are both the same value 2. And then we can produce a result. Now, it is important to note that this theorem has a name, so we can refer to that as a reason for why we can produce this result. And we would say by the squeeze theorem. And we have the result. The limit of g of t, in this case it was 2 plus t squared sine pi over t, must, since it is squeezed, have a limit as t approaches 0 equal to 2 as well, even though this function is undefined at 0. It is simply another function that we can make as close to 2 as we like by choosing values of t sufficiently close to 0. Now, if you do have a graphic calculator, or if you've got software like Maple, or if you want to use Desmos or something like that on a browser, try plotting this function, and you're going to see some very peculiar oscillations since it's a sine function, and because pi over t actually makes it oscillate faster as t gets closer to 0, it's going to have some particularly weird behavior. But you're going to find that the amplitude, that's how high it oscillates up and down, is going to start to condense and get squeezed towards the value 2. I'll leave that for you to try out on your own with whatever software or calculator you prefer. But I hope that helps at least explain why it's called the squeeze theorem. You can just mentally imagine something compressing this down into a particular value, and so the limit of the squeezed function must approach that as well. Thanks for watching. I guess I'll see you in the next video.